Welcome to the Chemically Dope podcast by AIChE-VIT, where we dive into the world of chemical engineering and connect with professionals, students, and chapters across the globe. In our season 1, we invited esteemed professors to share their knowledge and deepen our understandings within the realm of chemical engineering. While in season 2, we're bridging continents by interacting with AICHE student chapters worldwide. Today, I, Adya Saxena, Kathakali Mishra, and Sohail Kazi will be your hosts and are glad to welcome respected Dr. Yury Gogotsi, who will share his insights, experiences, and perspectives on the dynamic field of nanomaterials and MXenes. I think you're mute.
Okay, I'm
Katha,
so
your mic is
sorry.
off.
I'm so sorry. Yeah. Today's guest is a distinguished university professor of material science and engineering at Drexel University, as well as the director of AIChE-Drexel Nanomaterials Institute. His research focused on 2D material nitrides and carbides, aka MXenes, and other nanomaterials for energy, water, and biomedical applications. He has also made principal contributions to development of materials for electrochemical capacitors. He has published about 800 papers, which have been cited more than 1,800,000 times. He is recognized as a highly cited researcher in material science and chemistry, who has received numerous awards for his research, including the Ceramic Prize for the World Academy of Ceramics, MRS Medal, ACS Award in the Chemistry of Materials, to name a few. But aside from all that, he's also the child who never needed a textbook, memorizing every simple chemistry related topics by simply listening to his teacher. And he still is that guy that inspires us to love chemistry the same way. So it gives me immense pleasure to introduce our honorable guest speaker, Dr. Yury Gogotsi sir, who has graced us with his august presence at today's episode of Chemically Doped. Welcome, sir.
Thank you for the introduction. Glad to be here. Thank you very much for inviting me.
Thank you,
Sure,
sir.
we
We're
are
Pleasure.
glad.
honored, sir.
Always. It's sort of a bit of a fan moment for the three of us as well. And well, I'd like to inform our viewers that Dr. Gogotsi is also known as the father of MXene. Him and his team were responsible for the discovery of MXenes in 2011, and it was a path-breaking discovery in the field of nanomaterials, of course. But, sir, I want to know something. I was watching one of your interviews in which you said that the research that ultimately led to the discovery of vaccines was initially about lithium ion batteries. So, how and when did that research project of yours take a turn towards vaccines?
Oh, in real life, serendipity very often plays a role in discoveries. What it means that many discoveries are not made because someone planned it here. Moreover, it's very difficult to plan a discovery, especially like in the case of materials, no one expected to exist.
Right.
No one at that time knew that carbides, nitrides of transition metals can be made in two-dimensional sheets few atoms thin. But this is not just case for MXenes. Many chemical elements, many chemicals, many new materials were discovered in a similar way. What is important? When you are a scientist, you need to observe what happens when you do experiments and not only look for an expected result, but first of all, look for something unusual that happens. So, how happens with MXenes? We were working on developing electrodes for batteries. As you all know, lithium-ion batteries
Yeah,
specifically a
yes.
very, very popular topic nowadays worldwide, including India and the
Right.
United States, of course. And I had an idea that layered carbides, known as MUX phases, particularly titanium silicon carbide. When there are layers of titanium carbide and layer of silicon, being conductive, being layered like graphene, and containing silicon, which is a popular element in anodes that can store more lithium atoms per atom than carbon, would be a good electrode material. We received with my colleague, Professor Barzum, a grant from the Department of Energy, and we started experiment. And we got a very good student, Michael Nagib, who worked hard. He tried, and he could not get lithium to go in sufficiently large amounts. So, what we decided to do to make some space for lithium, basically imagine like a layered structures to remove some layers to make space that lithium can go in. We have been doing this for many years, making carbide derived carbon, so known etching away various elements from carbides. And when he tried many different ways to etch, finally he found that hydrofluoric acid
I said, yeah.
can etch max
Right.
phase. But what he got at the end were some kind of a dark, thin sheets, which we initially, after TM analysis, as, assumed was graphene. But then detailed analysis showed it was a new two-dimensional materials, titanium carbide in 2 dimensions, which opened the family of very large number of two-dimensional carbides, nitrides, carbonitrides, oxycarbides. Nowadays, people also make in a similar way borides, silicides.
Right.
So
Yeah.
basically, greatly expanded the family of 2D materials here. So you see, this is how discoveries happen. You need to be prepared to see what is new. You need to be interested in not only the goals that you set initially or your PhD advisor set for you, but also observe what you find, what happens. And whenever you see anything different, anything unusual, don't ignore it. Don't think, okay, this is not what my advisor asked me to do, deliver. Look, what is this? This may be your next big discovery.
All right. That was
That
a
makes
really
us look
happy
at things
session.
in different way too. Like
Mhm.
now, after a lot of things, we can look at things we might not have looked on in a different manner.
Yeah, it really changed
Exactly.
Thank you
my
for that
perspective
insight.
on
Mhm.
everything.
Yeah.
Yeah, so my next question is, in your interviews, you have frequently expressed appreciation for your team consisting of over 40 talented and hardworking individuals.
Mhm.
So I'm curious to know that if there is a current topic of interest or a shared goal that the team is collectively working towards,
Mhm.
or if the different members are focusing on various
Mhm.
research topics at present.
Mhm. Yeah. Well, as you realized, for example, in the case of MXene discovery, if there were no talented, capable of doing research student who made right observations, who was persistent in trying to achieve the goal,
Right.
there probably would not be a discovery. It doesn't matter how many ideas a professor has, unless there is a student, postdoc, another researcher who will go to the lab and test those ideas and make them
Right.
work,
Yeah.
nothing is going to happen. So
Right.
that's why the a discovery is very often a teamwork. Someone
Yeah.
provides ideas, someone does the synthesis in chemistry, someone conducts analysis. This is how research is done. So, MXenes, as you have already heard, are a very large family of materials. So far, about uh, 40, 50 stoichiometric MXenes have been reported. A couple of dozens of solid solutions have also been made. If you consider surface termination, oxygen, hydroxyl, halogens, chalcogens,
Right.
you can again increase this number by dozens of materials. However, About 1,000 of stoichiometric compositions are possible if you consider all the metals, X elements, carbon, nitrogen, oxygen, and all the surface terminations possible. And infinity if we consider mixing different elements on M side, metal side, X side, or on the surface. So what we do, we continue discovering new MXenes, making new materials, characterizing them, and of course, if there are so many of them, any number of students, postdocs can be involved. For example, just last week, a master student, actually BSMS student who did a bachelor master study at the same time, Marley Downs from my group, graduated, and
Yeah,
she produced a couple of new materials during her study,
that's
being an undergraduate student. So you can do discoveries at any stage of your career. You don't need to wait till you become a senior researcher. And there are other people who focus on analysis, characterization of those materials. We did not know how Raman spectra or infrared spectra of MXenes looked like. And we nowadays know many of those. We know how to identify them. We still need to characterize many more. And finally, we need to study properties, how conductive they are, how strong they are, what are their electrochemical, chemical, optical properties. So there are students and postdocs who work on this topic. We have also, after characterization of properties, an opportunity to find practical use. MXenes that have high electronic conductivity can be used, for example, as conducting inks. They easily disperse in water, pure water with no surfactant, and we can print devices. We can print circuits, we can print supercapacitors and sensors and so on. Some other materials have very interesting optical properties. For example, niobium carbide absorbs infrared light in exactly region where it can be very, very efficiently heated with almost 100% light to heat conversion efficiency. And
oh,
it's being explored for photothermal therapy, treating cancer, destroying cancer cells, or photothermal water desalination. And there are many other materials that have many other useful properties. So other people work on um, exploring those properties. But what is important? They don't work separately, like 40 people, everyone has own projects and don't talk to each other. They collaborate. So as a result, everyone's work is accelerated.
yeah,
And we can move faster than many other research groups exactly because of this wonderful community of people. And what is most important, they also learn from each other.
yeah,
They learn about science because we have people with physics, chemistry, mechanical, chemical engineering backgrounds in the group. But they also learn about life, about different cultures. Just yesterday night, we had a party celebrating the end of the academic year, end
yeah.
of the
Right.
quarter, graduation of PhD students, uh,
Wonderful.
faculty position for a postdoc who are leaving. And we all had fun together. And that's again very, very important. This is a part of the education, cultural experience, multicultural experience. We have people from at least a dozen of countries in our group, and learning how to be a scientist. So we work as a team to solve both scientific problems, but also grow professionally.
That's
That
This
great.
is
shows to
nice.
go how far a scientific community, the sense of a community can take you is just incredible.
That's absolutely true.
Yes,
Is there
it's
something you are personally working on yourself right now?
Well, well, I do. Well, I do write sometimes papers myself, but those are not really research papers. Those are editorials,
Right.
perspective article where I present my vision of science, or my opinion about a certain topic, for example, scientific publishing. And all the other work I do together with students, postdocs, and also collaborators. I work with people in many different countries. And this is a very productive team. So pretty much I read, edit a paper per day. We discuss ideas with my students every day. We discuss results obtained. So it is really a teamwork, and I generate new ideas and we develop them together. And sometimes the results are good, sometimes they don't work, but you don't know until you test the idea, until you experimentally
There might
verify
be
it.
another serendipity. We never know.
Exactly, exactly. And sometimes again, we look for one material, one property, and find something else. And it takes our research into a new direction. And in my personal career, almost all changes of research direction happen exactly as a result of such a serendipitous discoveries, from switching from ceramics to carbons, to studying phase transformation and contact loading, discovering new phases of silicon. So you find something new. You should be ready to switch. You should not stiffly follow the path initially outlined. If you find that what you have observed is more important than something you initially planned to study, you should not be afraid to make a U-turn and go in a different direction.
Yes, it really motivates me and gives me hope to see that even though people do know sometimes what they're going to do, but in the case of some students, like students of today, or maybe myself, if I talk about, we don't really have an idea right now, even though we are undergraduate students, of what we are researching next, or if the research that we are currently pursuing will give us the results. But seeing your discovery and the result you have got, I feel really motivated to pursue anything in this field right
Mhm.
now.
Yeah. What is also important, you need to look for a research topic in general that is of interest to you. If
Right.
you're interested in organic chemistry, work on organic materials. If you're interested in inorganic chemistry, work on novel nanomaterials,
Yeah.
ceramic materials, wherever you can find something that you like, you feel and understand. If you are motivated by making environment cleaner, work on environmental chemistry. There are numerous opportunities. What is important is that you find as a young researcher something that you like, something that you feel is your destiny, and pursue it and enjoy research, and your discoveries will certainly happen.
Yes, sir. I will definitely take your advice and
Mm.
then, yeah, continue doing my research. So, for my next question, so basically, I read that the second international conference on vaccines was held in 2019 at
Mm.
Beijing, at the Beijing University of Chemical Technology in China,
Mm.
and they covered numerous aspects of basic science and application of vaccines, including their synthesis, properties, structure, as well as applications. Then a symposia happened in Europe, United States, then China, which was scheduled for 2020. But
Mm.
can you tell us about any more such events which may be happening in the near future, which might bring some spotlight on the present vaccine research and developments in this field?
Well, research in MXenes grows exponentially,
Mm.
very, very quickly. So, just this year, uh, we will have the third international conference on vaccines at Drexel University in the beginning of August, August 5th to 7th. And there will also be an opportunity to participate online. So I would like to invite everyone. But
Yeah.
in 2 weeks, I will be in Europe speaking at the EuroMaxine Congress in Spain. So there is a dedicated MXene conference. There will be another MXene symposium at the European Materials Research Society in September. In October, there will be the 5th International Conference on MXenes in China, in Xi'an, and the organizers told me they expect about 2,000 people joining that conference.
That's
And
great.
this is not surprising because there are tens of thousands of researchers who already published papers on MXenes. If you look in the trend of publication in Web of Science or Scopus, you will see that MXenes currently grow faster than any other 2D materials or nanomaterials in general.
Right,
Number
right.
of publication on materials studied earlier like graphene, silicene, germanium are dwindling, slightly slowing, going down. MXene number of publications still keeps growing very quickly. So what does it mean? There is growing interest, and it is justified by outstanding, absolutely unique properties, where MXenes outperform other known materials or greatly complement them, allowing
Mhm.
new applications, allowing us to create combinations of materials with properties that no other known material today can deliver. And this is what drives further research and development. So there are many events, there are symposia, many conferences, including, for example, the Graphene Conference, Graphene 2024 in Madrid, including many other professional society events, including American Chemical Society. So, and I'm sure there are events in India because
Yeah.
India, in the number of publications last year, I think already has overtaken the United States. Even so, 5-6 years ago, very little was going on in India, and now this is clearly a very popular research topic.
Yes, sir.
Absolutely.
It's
Actually,
really.
nanomaterials as a subject has been an area of interest which has been exponentially growing in the just recent couple of years. It was not a
Mm-hmm.
very well discussed topic previously, but then again, in a couple of years span, it just exponentially boomed, and people have started to take interest, and that is, I think that
Mm-hmm.
is why there have been a number of publications, and
Mm-hmm.
it's just wonderful to see.
Fully
Yes,
agree.
considering the many applications, and I feel like as an individual myself, I feel that I want to work in something which is related to sustainability and environment research. So my next
Mm-hmm.
question is related to that. So I just wanted to know that how can nanomaterials like MXenes contribute to the addressing global challenges such as energy scarcity and environmental degradation? And are there any emerging trends in the nanomaterials and energy storage that you might believe will shape the future of this field of nanomaterials and vaccines
Mm-hmm.
as well?
Thank you. This is a very good question. And this is a question we always, as scientists, should ask ourselves. How do materials we make contribute to solving important problems? And
Right.
as you already know, we discovered MXenes because we were searching for better materials for batteries.
Right.
And electrical energy storage remains the key issue in switching from fossil fuels to solar, wind, and other renewable energy sources. So we'll all look for better batteries, let's put it this way.
All right.
But conventional materials have certain limitations. One of them, for example, when you work with bulk materials, there is solid state diffusion, which
Mm,
limits our ability to charge batteries quickly. As
yeah.
a result, you have to plug your cell phone overnight to get a charge. Your computer requires a couple of hours to get charged. It's
Right.
especially, of course, important when, say, you have a car, you want to recharge it quickly.
Right.
So, ways to charge faster, minimize solid state diffusion. In nanomaterials, all redox reaction happens on the surface. So potentially you can charge very quickly. So if you want a fast charging batteries, we need nanomaterials. Second, what does it mean fast charging? This means simply running a high current through your battery. Even chemists know the Joule law, that Joule heating will happen when you run a high current through a poor conductor.
Yeah.
So materials used today in battery supercapacitors are not extremely good conductors.
Yeah.
Titanium
Right.
carbide MXene has electronic conductivity about 2 to 3 orders of magnitude higher compared to activated carbon, for example, using the fastest energy storage devices, supercapacitors.
That's great.
So, if we use these highly conducting new materials, we can charge batteries faster because 2D materials are flexible. We can make flexible, wearable batteries for future personal electronics, for epidermal electronics, wearable devices embedded in textiles that we wear, enable new opportunities. But also, think of environment. What happens when your computer battery produces heat? And I'm sure when you use your computer, your cell phone, charging it, you feel heat goes. It
Yeah.
means
Right.
wasted heat.
Right.
And it is wasted largely because you are charging materials with low conductivity. So we will not only able to charge faster, but we will able to charge with less weight. So this is one of very important application. But I can switch to another one. When you have two-dimensional materials, you can make very, very thin and very well controllable slit pores between the layers. And you can use membranes made of MXenes for water desalination,
Yeah.
separating ions from
Right.
water,
Right.
producing drinking water, or removing toxic ions from water. You can also use it for gas separation. If you want to produce hydrogen, you need again to separate it. People consider transporting hydrogen along with natural gas, same pipelines, and you need a kind of a filter that allows you after that to separate hydrogen from methane. And MXene's membranes are capable of this very fine tuning because taking different chemistries, taking different materials with layer thickness and interlayer spacing, you can design membranes with very, very high accuracy. So you see, water and
Right.
energy are two of the very important applications. And there are applications in solar cells for electron transport, whole transport layers, again making thinner, transparent, highly conducting, and flexible cells. And those are applications we are pursuing ourselves or with collaborators. And we hope to contribute to making the environment cleaner, better, safer, and slow down the global warming.
Right, right. So, as I had seen, I was just researching on vaccines, and I thought about that it was such a futuristic material that you had said some problems about the in the world there were 15 or 16 problems, and just a 2D material could solve all of these problems in other applications as well. So it's really amazing to see your contribution to the industry and to the environmental industry as well, because it's really a futuristic material that you have come up with. So,
Well, thank you. But let me also mention something. Uh, once there is no material that can solve all the problem.
right.
So new materials contribute. We will keep using older, already known to us materials. You know, we're out of the stone age, but we still use stones to build,
Of
right?
course.
Right.
Of course.
Things here. So similarly, but new materials open new opportunities. We
Right.
would not have our computers and cell phones without new materials.
Exactly.
Right. And this is where we believe two-dimensional materials. MXenes will take us into era when we will have flexible, transparent electronics, embedded devices,
Hmm.
devices which are much smaller than we use today. That will allow us health monitoring of people by again this epidermal sensors that can take all the vitals and send them to a supercomputer, having more knowledge than any good doctor. And this type of health support will be available to everyone because it won't depend on the distance. And long as there is a cell phone connection, someone in the remote village in India will be able to get the same qualified medical support as someone having a lot of money and access to the best
Right.
Healthcare.
hospital in
Right.
New Delhi or elsewhere.
Right.
So I think that's how you need to look into this, solving new problems, adding new capabilities that current materials cannot deliver.
Right.
After hearing about this topic of discussion, actually, I would like to ask you something
Mhm,
regarding this very topic. You just said, like a few minutes before, that a scientist should always think about how his or her discovery is affecting the day to day lives of people and how it's contributing to the lives of people. So, I would like to ask that vaccines have so many applications, like various, like more than like 12, 13, 14 applications which can be actually used in day to day
mhm,
lives. But my question is that is all the applications being used to their full utility? And as a scientist, are you
mhm,
satisfied with the way it has been used, or do you think that there is much more potential
mhm.
and much more
Well,
things can be done?
yeah, this is an important question. Yes, there is much more potential. No, I'm not satisfied with the current progress because a scientist should never be satisfied with result achieved. Scientists should always look for further developments. But the reality is that when you discover a material, you learn about the properties. And based on properties, you consider, okay, where is this material useful? So if material is able to absorb light efficiently and transform it into heat, yes, desalinating water is a great application. Treating cancers instead of gold plasmonic nanoparticles using much less expensive, easily dispersible in water and biological solution, MXenes is advantageous. But new applications appear all the time because why it's important to publish research? Because people somewhere, maybe on the other side of the globe, looking at this material, can identify a problem that they can solve. For example, we published recently a paper on making lightweight, lower cost waveguides for satellites.
Oh,
Hmm.
okay.
Very
Hmm.
far from my area
Wow.
of research, but
But yeah.
a researcher in Canada, knowing properties of MXene and working in the field of communication, particularly for space application, knew there is a problem because waveguides that connect source of um, microwave energy radio waves to antennas that allow satellite communicate with Earth are made of metal. So they're considered to be heavy metal pipes, which need to be very well polished inside, have complex shape, and they need to transfer microwaves to antenna. So nowadays we can print them using a cheap polymer, for example, nylon, just deep
Right.
coat in a MXene, and it works pretty much like a metallic waveguide. It's 10 times lighter,
Right.
and since those waveguides are very expensive to produce and cost thousands of dollars, also less expensive, even with the cost of material today. And I would never come up with such an application because it's so far from my field. I did not know that even such a
Right.
need exists. So it means that new application will be discovered as people learn more and more about those materials. And in the
Right.
beginning, it's virtually impossible to say where, in what field, a specific material will make a big impact. When silicon was discovered and made as a pure element, no one had an idea that the electronics will be based much later on silicon. Diamond-like carbon, when it was initially developed, was considered a semiconductor electronic material,
Right.
but it was used to coat all the hard drives for decades, enabling energy storage in the computers. So I think when we make new materials as scientists, material chemists, we need to present them to community, describe how to make them, describe their properties, and let people working in different fields explore applications. So I know about some application like electrochemical energy storage. This is my field, but
Yeah.
I know very little about waveguides for satellites
Mm-hmm.
or many other applications where people explore MXene today for thermal management, preventing heat loss from
Right.
equipment,
All right.
microwave application in antennas, tunable antennas, for example, or even cancer treatment. When I understand that photothermal therapy is very important technique, but I'm not a medical doctor, I am not a specialist in cell biology or
Yeah.
cancer treatment. So this is exactly specialists need to work. But if material chemists work directly with people who explore applications, we can get together to the end goal faster because we know how to design and tune materials for applications, not just let them take a commercially available already material and try it, because nanotechnology is not about making things small. It's about controlling properties and behavior of materials and nanoparticles at the nanoscale. And this is what we are doing in our research.
Right. After hearing about the number of applications, not only in just one particular field, but in a diverse array of fields, it just shows you how one discovery can be path-breaking, not only in one area of life, but also just in general make life a better place for everybody. So, regarding that, I would just like to ask you. eh, what do you think about the accessibility of MXene as of now, so
Yeah.
that people could actually come up with different sorts of research?
It is limited because whenever a new material appears, it takes time to scale it up.
Yeah.
Moreover, until there is an obvious large scale application, no one is going to produce tons of the material.
Right.
However, what is important? You can buy already MXenes from a large number of companies. For example, Carbon Ukraine was one of the first companies commercializing MXenes. They have a license from Drexel University, and I know have been supplying many researchers in India with max phases, precursor to MXene, and nowadays MXenes. There are companies in Korea, in
Right.
UK, in US. My students recently started a company, MXene Ink, to manufacture printable inks. There are many companies in China. I'm not sure if there are companies in India. I'm not aware of licensing technology from Drexel University in India, but I hope there will be. So,
Yeah.
and there
That's
are
great.
big companies like Murata Japan, which already scaling up MXene for their application, for their product to very large scale manufacturing.
Right.
So materials are available, but this is as need increases, the manufacturing volume will also increase. What is important? MXene's technology is intrinsically scalable. Whether we talk about wet chemical etching, emulsion salt etching, or chemical vapor deposition like a fluidized bed, CVD, because it really determines by the size of the reactor. There are processes like a two-dimensional CVD, which is very difficult to scale up to tons and millions tons. MXene synthesis can certainly be scaled up to virtually any volume. Even in our laboratory, we demonstrated making kilogram batches of MXenes. So what it means that whenever people are ready to start introducing products, materials can become available. And I think this is how all this technology goes. People make small amount of materials, there is application, people start manufacturing large volumes, and as volume of manufacturing increases, the cost decreases, and also application appears in the field where initially the cost was prohibitive. So medical, space applications, electronic application are usually the one you start first because they require small amount of materials and performance is more important than cost usually. And
Right.
then as materials start being produced, they penetrate other fields and become eventually a commodity, so they can be
Correct.
used everywhere and produced at
Commercial.
very low cost.
Correct.
Yes.
So, with that, I think that is all we had to ask you, sir.
Mhm.
No,
And
I would like to add another question.
oh
Actually,
yeah, go on.
this
Sure,
made
sure,
me wonder
sure,
something.
sure.
Actually, I was thinking about this one question, that what is right now the most in demand application of MXene? Like, what is mostly being used as of now?
Electromagnetic interference shielding is probably is the one that is the most critical. So every device you use, cell phone, computer, components in your cell phone, they need to be protected from crosstalk, from interference from other electronic components. And MXenes appear to be titanium carbide MXenes particularly the most efficient materials for shielding, better than metals used, and they can be used in very thin films. So, for example, 1 micrometer film of titanium carbide can uh, reflect 99.999% of microwaves. So it and this is great because one can make it 10 times thinner than a metal cage that is used currently in, say, electronics, or sometimes it's even much thicker metal layers. So, and it will be important specifically for thinner wearable electronics where one needs very, very thin layer for protection. So this is kind of a probably application being explored by many in many countries, and it requires fairly small amounts of materials. So it became the most popular one. Will be
Right.
the one stay in the leading application? I don't think so. I'm sure there will be many, many other
What do you
applications
think might
emerging.
be the one more growing? Like,
I don't want to make predictions because my experience and history of science tells that it's impossible to predict. Many materials found applications in the field where no one initially thought of them. I'm a very strong believer in epidermal electronics. I
Mm-hmm.
believe that this is how all the medical diagnostics will be done in the future. And vaccines have lower impedance with skin. So it means that it's better than gold, higher conductivity than reducing graphene oxide and carbon materials used. So it's by far, in my opinion, the best material for use in all the epidermal electronics. And I believe this will be an area which will determine our future in terms of healthcare. And I think this is a very, very important application, in my opinion. But it's very possible that someone will come with a great idea how to use vaccines in some other different application. For example, produce cleaner and less expensive energy using sunlight. And it's very difficult to predict where new materials will go. What's important that people learn about these materials,
Right.
understand their property,
Correct.
structure, chemistry, and think what those materials can do, and then try. And again, an application can emerge also as a result of this serendipity. You may explore it thinking one application and find that it actually can work
something
better in a
else.
totally different one here.
Right.
So, and this is what the excitement of discovery science. You never know exactly what you will find out. It's imagine like you go to a forest searching for some fruits or mushrooms or something else. You don't know where you find them. You don't know if
Right.
you find them, but there is a probability you find something useful, tasty, interesting, unusual. So let's keep searching as a community. Let's keep doing discoveries and try to use our discoveries to make the world a better place to live.
Of course, Doctor, that was really encouraging words. And on behalf of the three of us, I really thank you a lot. We're truly grateful. It was an incredible experience talking to you, having this wonderful conversation, not only
Mhm.
in a professional context, but also in a personal capacity. For the three of us being undergrad students, talking to you, having this wonderful chat. It was a humbling experience, especially when you receive such warm, welcoming energy from a person of such a high status in the scientific community. It was just incredible.
Well, it was my pleasure. Undergraduate students are the ones who will be building the future. You are the
Sure
ones
enough.
who should bring new ideas, and I wish you and your audience all the best. I wish you your own discoveries, and science is exciting. Trust my many years of experience in science,
Of course,
and
Right.
sir.
all together we can solve many problems in this world. Thank you very much again.
Thank you,
Thank you.
sir.
Thanks a lot, sir.